So now we're actually going to look at one of the available high-quality implementations of these algorithms. The software package called MoveIt, which is open source, contains high-quality implementations of many motion planning algorithms, RRTs, PRMs included. MoveIt contains a lot more than just those core algorithms, and in fact, it often uses the core algorithms from external sources as well. But what it does is it brings all of them together into one package, and it allows you to run them as it has interfaces to various robots. It allows you to do collision queries and so on. And in fact, I strongly recommend going to the MoveIt webpage, learning about the underlying planning packages that it relies on, again, which many of them come from different sources, from academic labs, from industry. Some of them were actually written by the authors of MoveIt, and checking out all the examples that you can find there. You'll see many cool examples of motion planning on robots. I think MoveIt has been used on dozens and dozens of robots so far. So I have MoveIt running on my laptop, and I can use it on a simulated robot. I have a workspace set up for that. The simulated robot that we're going to use is a simulation of the Baxter robot, the Baxter made by Rethink Robotics. The Baxter has two arms, each arm with 7 degrees of freedom, so you could be planning for both arms simultaneously, and then it becomes a 14-dimensional planning problem. However, to make things a little simpler, we're only going to use a single arm here. So let's say we're going to plan for the left arm. So you can ask for new positions for the arm, and the ghosted transparent orange arm shows what I'm asking the arm to go to. Let's say I ask for this position in free space. I'm going to slow down the paths a little bit so that we can better visualize what's happening. And then MoveIt will plan a path and show us the execution of the path that gets us from the start to the goal. Pretty simple path here, no obstacles really to speak of. Let's make things interesting. Let's import an obstacle. So now this pillar, let's say, represents an obstacle. And I'm going to ask MoveIt to find a path that gets the arm starting from one side of the obstacle and gets us to the other side. So it'll look maybe something like this. And then it finds a way to go over the obstacle and to the other side. Let's do it again. Let's move back to our original side. Maybe go down a little bit. Again, where we're starting from is in red. Where we want to end up is orange and transparent. We're asking for a plan and the execution, and you can see that it finds the path that takes the arm over the obstacle and ends up exactly where we've requested it to go. Sometimes the path will take what looks like some unnecessary zigs and zags. We saw maybe some of those in this last execution. MoveIt will smoothen and shorten the path and take shortcuts and in general do the processing the way it's supposed to be. RRTs, stochastic motion planning in general, do have that characteristic that sometimes the path isn't what would seem optimal. So let's plan for a new path. Up and over. And gets to the destination. And again, I strongly encourage you, if you have ROS installed on your computer, to go ahead and get Move It, and then there's a variety of simulated robots you can play with and get a sense for what the motion planners look like. Move It, again, can use many motion planning algorithm implementations. It'll have RRTs, it'll have PRMs, so you can get a sense for how those work. And it will solve what looks like pretty complicated planning problems, robot reaching into tight spaces or coming out of tight spaces. So let's recap the motion planning, the part of it that we looked at today. And we phrased the general motion planning problem as this idea of searching for a path from a start, a current configuration of the robot, all the way to a goal or a desired robot configuration. Obviously, that has a very clear correspondent for mobile robots, right? The robot is at a current location in space. You'd like it to get somewhere else, and then there's a map on the way which shows you the obstacles that the robot must avoid. Interestingly, the problem is phrased the same way also for robot arms. So articulated robot arms that start in a current configuration, you'd like the arm to end up in a different configuration. You'd like it to not hit anything along the way. And it turns out that if you reason about this not in Cartesian or task space, but rather in the configuration space of the robot arm, it ends up looking a lot like finding a path for a point from a start to a goal, avoiding a bunch of obstacles along the way. So we've talked about configuration space, how to build configuration space, the configuration space of a robot, what it means, and how to operate in C space. So once you think about the problem in C space for robot arms, and then for mobile robots, you think about it in Cartesian space, then motion planning becomes really the same problem of finding a path from the start to the goal. But then, once you start looking for ways to solve the problem, then these two cases start diverging again, just because of the practical implications of the nature of working with mobile robots versus robot arms. With mobile robots, the space that you're searching in, which is Cartesian space, tends to be low-dimensional, maybe two-dimensional, three-dimensional in some cases. On the other hand, for robot arms, these spaces can be very high-dimensional. If you have a robot arm that has 6 joints or 7 joints, then the configuration space is 6-dimensional or 7-dimensional. That means that it's difficult to build representations of the obstacles in this high-dimensional configuration space. If you want to discretize your configuration space and represent it as a grid, a 6-dimensional, 7-dimensional grid is something that's computationally intractable to keep track of and to use. So because of the different nature of the dimensionality of the problem, we tend to have different types of algorithms that solve motion planning for mobile robots versus motion planning for robot arms. We will talk about mobile robots in next lecture. This lecture we focused on motion planning for robot arms. And a very common solution for motion planning for robot arms with many joints is this family of sampling-based algorithms. These sampling-based algorithms, they share a couple of very interesting characteristics. They fundamentally rely on the ability to sample random locations in configuration space. Because of the randomness, we also sometimes refer to them as stochastic motion planning algorithms. And furthermore, you don't need actual representations of the obstacles in your configuration space. All you need to do is, if you sample a particular point in configuration space, you just need to know, hey, is this point valid, usually meaning in collision with something, or not? And then if you have this ability, then even if you have 2 points in configuration space, you can also check if the line between them is valid or not by sampling many points along that line and checking if each of those individual points is in collision or not. So sampling-based motion planning algorithms use this ability to sample random points and just say, are these points in collision or not, and use them for a random exploration of the configuration space, which eventually ends up connecting your start to your goal. At a first look, it can seem that the random nature of it is going to be a problem, but it turns out in practice that this random exploration is extremely, extremely powerful, especially for high-dimensional robot arms. And we've looked at 2 examples of sampling-based motion planning algorithms, RRTs and PRMs. We've looked at the implementations of those, but then we've also checked out high-quality, essentially industrial-grade implementation of sampling-based motion planning algorithms, which are available as part of the open source Move It software framework, which is an excellent entry point for playing with, getting a sense of how motion planning algorithms work for robot arms, and it's integrated with ROS, so you can always download it and try it with various robot models and get a sense for how motion planning algorithms work. So this was primarily focused on robot arms. Next week, we'll also talk about motion planning for mobile robots.